So in this video, we are going to see how to detect if x is a perfect power of 2, like 2, 4, 8, 16. Okay, so here is the logic. Uh, bool f equals x and x minus 1 equals 0. If this condition is true, then that means x would be a perfect power of 2. Now, why this works? Because if you see the binary representation of the perfect power of two numbers, they just have one bit set. Okay, so for example, take 2. 2 is this in binary, okay? And then let's say 4. So this is the binary representation of 4. So you can see all the bits are like 0 and only one bit is set. So let's take 16. So 1, 2, 4, 8 and 16. So this is just the binary representation for 16, and again only one bit is set. What happens when we do x minus 1? So what happens, what is the representation for 15, for example, in this case? So 15 would be 1, 1, 1, 1 and 0. So you can calculate this and see. So a number less than a perfect power of 2 would have all the bits set as 1, but not the bit that is set for the perfect number. Okay, so what I mean is 16 has this 1, 2, 3, 4, fifth bit set. Okay, this one would have fifth bit as 0 and 1, 2 to 4 bit set to 1. Okay, so if you see any number like 4 has third bit. Let's say 4 has third bit set to 0. So what happens with 3? 1, 1, right? Like uh, everything less than the third bit is set to 1, and 4 and the third bit is set to 0. Okay. So what happens when we do a bitwise AND? So now you can see, if there, always there will be a situation something like this. If we do x and x minus 1, so this is for 8. This is a binary representation of 8, and this is for 7. If we do a bitwise AND, so everything is 0, right? So that's why our logic is, if x and x minus 1 equals 0, then this would be true. And that's how to detect a power of 2. There are few things, however, we can remove that equality comparison. How? So we would do bool f equals x and x minus 1, and remember this would give me 0, right, for if x is a perfect power of 2. So what I want is this variable to be true or 1 in case of C. So what I would do is I would just add a negation here. Okay, so this one would also work. um, Next thing, what happens with 0? Like when x is 0, what happens to this? So 0 and minus 1, right? So this one again becomes 0, and then f would be 1, right? Because 0 and 1 would be 0, and then this negation would turn false into true. So 1. But remember, the 0 is not, we don't want to consider 0 as a perfect power of 2. So what do we do? How can we handle this situation? What we do is we'll add just one more condition. So bool f equals x and negation of same condition, x and x minus 1. Okay, so now this can handle the condition for 0, because when it's 0, this is a short circuit. This is not a bitwise AND, this is a logical AND operation. Okay, so this one would short circuit. The later part of the operation is not evaluated in case of logical AND if the first expression is false. Sorry. So this one, in case of 0, this makes this entire expression as false, and hence this becomes 0 or false. So let's see everything else in the code. So this is the code. This is the first version or the second version, what we discussed in theory part. Let's see how this works. So we compile it and then run it. So x is a power of 2 and x is 16, so that's fine. Okay, let's try to run it on something which is not a perfect power of 2. So this is not a perfect power of 2, so this is working fine. But if you see the case of 0 here, X is a perfect power of 2. So which we don't want. We don't want to consider X, 0 is perfect power of 2. Okay. So what we would do is we would say X and this expression. Now see. So this gives X is not a perfect power of 2 and everything else would work. Okay. So that's it for this video. Thanks a lot for watching.